you here today, and thanks to Michael for the invitation. I wanted to address the idea of Promethean justice for mankind. Mr. LaRouche has really been stressing recently what the identity of mankind has to be and what kind of culture would be able to solve the problems or would naturally solve the problems that are confronting us. So, Pat just covered a very, very dire situation regarding the drought. And you think there's a lot of problems that used to be problems that no longer are today. For example, we don't have people saying to themselves, gosh, I have no idea when it's going to be summer. I don't know when fall's going to come. Is it going to be in 2 weeks? Is it going to be in 20 weeks? I have no idea. That doesn't happen. We have calendars. That's like a problem that's so old you wouldn't even think about it. Or how could we move things easily? Oh, we could use a wheel. That's not a problem anymore. That's a thing we know what we're doing with that. It's not tough. There's other things like that today, like for example the idea of agriculture, of planting seeds so that you'll then find crops to eat later. That's not a mystery. That's not surprising. That's just kind of obvious at this point. The daily cycle we've overcome to a large degree. Day versus night. I mean, not on broad areas, but we've got electric lights. We can see things at night if we want to. We have factories that can work 24 hours a day. Even the yearly cycle, not for agriculture, but we have heating, we have cooling. So there's a lot of problems that, at least for some of these in the more developed countries, aren't problems anymore. For what kind of society would water not be a problem? Would the weather be something that would be so naturally controllable by us that we wouldn't give it a second thought? Just like we don't really think about how difficult it was originally to figure out the calendar, or know what the moon would do in the future, or use wheels, or use fire. So how will that become obvious? To get at that, I'm going to put this in the context of the fight between Prometheus and Zeus. Prometheus, there's a story about this that best comes from the Greek poet and playwright Aeschylus. As the story goes, Prometheus was one of the Titans. He was immortal. He was like a god. And Zeus, who was the head of the Olympian gods, wanted to destroy mankind. He really wanted to wipe us out altogether. And he was certainly angry at humanity and said that there is no way human beings were going to use fire. Forget it. That was for him. It wasn't for people. Prometheus took that fire, gave it to mankind, and boy was Zeus pissed. Because Zeus was the original, historically in this sense, oligarch. So I'm aware that some of you may have heard these quotes on Wednesday, but you know what? You can hear them again. They're great. So I'll put these up here. This is how Prometheus is describing his plight to a chorus that comes to visit him. He says, "However, you ask why he torments me, and this I will now make clear. As soon as he had seated himself upon his father's throne, he immediately assigned to the deities their several privileges and apportioned to them their proper powers. But of wretched mortals he took no notice, desiring to bring the whole race to an end and create a new one in its place. Against this purpose none dared make stand except me. I only had the courage. I saved mortals so that they did not descend, blasted utterly, to the house of Hades. This is why I am bent by such grievous tortures, painful to suffer and piteous to behold. I who gave mortals first place in my pity, I am deemed unworthy to win this pity for myself, but am in this way mercilessly disciplined, a spectacle that shames the glory of Zeus." This punishment he's describing, Zeus had his couple of his henchmen grab Prometheus, take him up to a rock high in the mountains, chain his arms and his legs and his chest, drive a stake through him to attach him to this rock, so he's stuck there, and Zeus, in the form of an eagle, comes and eats out his guts every day. And Zeus has said that's where he's going to stay until he recants, until he joins Zeus, until he tells Zeus some things that he wants to know. And Prometheus says, no way. When one of Zeus's henchmen comes to Prometheus and says, what have you done to yourself here? You're not in a good shape. Why don't you just, apologize? Zeus will forgive you. Prometheus says, no way, because I don't want to be a slave. You think you're, sitting pretty. You think you're free because you're not chained to a rock. You're a slave. I'm free. So the chorus goes on. They say, iron-hearted and made of stone, Prometheus, is he who feels no compassion at your miseries. For myself, I would not have desired to see them, and now that I see them, I am pained in my heart. Yes, to my friends I am indeed a spectacle of pity. Chorus asks, did you not perhaps transgress even somewhat beyond this offense? Says, yes, I cause mortals to cease foreseeing their doom. A second here. Chorus, of what sort was the cure you found for this affliction? I caused unseen hopes to dwell within their breasts. A great benefit was this you gave to mortals. In addition, I gave them fire. What? Do creatures of a day now have flame-eyed fire? And Prometheus says, yes, and from it they shall learn many arts. So he then goes on to describe what these arts are. Because Prometheus gave fire, but that wasn't the only thing. Prometheus is the creative identity of mankind. And he goes on to describe the many other arts that we get from fire, as well as the other boons of knowledge in addition to it. So here's what he goes on to say. He says, still listen to the miseries that beset mankind, how they were witless before I made them have sense and endowed them with reason. I speak not to upbraid mankind, but to set forth the friendly purpose that inspired my blessing. What were people like? First of all, though they had eyes to see, they saw to no avail. They had ears, but they did not understand. But just as shapes and dreams, throughout their length of days, without purpose, they wrought all things in confusion. They had neither knowledge of houses built of bricks and turned to face the sun, nor yet of work in wood, but they dwelt beneath the ground like swarming ants in sunless caves. They had no sign either of winter, or of flowery spring, or of fruitful summer on which they could depend, but managed everything without judgment, until I taught them to discern the rising of the stars and their settings, which are difficult to distinguish. There's the calendar, right? He says, yes, and numbers too, the chiefest of sciences, I invented for them. And the combining of letters, creative mother of the muses' arts with which to hold all things in memory. I too first brought brute beasts beneath the yoke to be subject to the collar and the pack saddle, so that they might bear in men's stead their heaviest burdens. And to the chariot I harnessed horses and made them obedient to the rein. It was I, and no one else, who invented the mariner's flaxen-winged car that roams the sea, the sailing ship. Wretched that I am, such are the arts I devised for mankind, yet have myself no cunning means to rid me of my present suffering. Chorus talks to him. It keeps going. He says, hear the rest, and you shall wonder the more at the arts and resources I have devised. This first and foremost. If ever men fell ill, there was no defense, no healing food, no ointment, no drink. But for lack of medicine, they wasted away, until I showed them how to mix soothing remedies, with which they now ward off all their disorders. And as to the benefits to men that lay concealed beneath the earth, bronze, iron, silver, and gold, who could claim to have discovered them before me? No one, I know full well, unless he likes to babble idly. Hear the sum of the whole matter in the compass of one brief word. Every art possessed by man comes from Prometheus. So I think that sets the stage for who Prometheus was as a person. You get a sense of what all of these arts were, all the things that we take for granted. As saying before, medicine, for example. Smallpox has been eradicated today. So let's look at this specific kind of fire. Now, fire really stands out among technologies because it made possible an entire domain of potential that didn't exist before it, and we're going to get into that. To start off, I wanted to show a measurement of different kinds of fire. So here you see this chart. We've got what you see going on over time is a development of the amount of energy used per person in the United States over the history of our nation. Two things stand out. One, we're using more energy per capita over time. The second is that the dominant source of that energy has changed over time as well. Wood was, I mean, there's a lot of wood that was used early on. We don't use very much wood anymore. People might, have a fireplace for, an occasional interesting evening, for ambiance or something. Some people use it for heating their homes. Not a lot. It's just fallen away with the development of coal first, and then coal has somewhat declined in importance relative to oil and natural gas. What are the reasons for that? Coal replaced wood for heating, for sure. It's just it's much easier to get, and it doesn't run out as quickly. Wood becomes scarce pretty quickly if you've got a growing population. Some of the first environmental legislation in history of mankind came about 700 years ago in France, when laws were passed to protect forests because they were all being chopped down to be turned into charcoal. With coal, you save trees. Then think about oil and natural gas. It's a higher form of power, both in terms of what it can do and its density. There's more energy per pound of oil than there is in coal. You couldn't run an airplane on coal, for example. Also, you have internal combustion engines with petroleum. You don't have that with coal. You do have a steam engine, but internal combustion engines are better. And then this tiny sliver that you see right here, this little bit, you can barely see it probably, that red bar, that's nuclear power. That's fission. That's how little the share of nuclear power is in our economy today. Tiny. This is total energy, not just electricity. Very small. This is where John Kennedy's administration thought we would be by now. Look at that, over 50% beyond where we are today. And this is where we might have been had we been on track to developing fusion and fully developed fission before that. So why is there so little nuclear power? What happened? Well, it has to do with this guy. Zeus, the empire, the oligarchy. Fears about nuclear power, I mean, I'm not, it's just kind of silly stuff. We're going to talk about what nuclear power is a little bit later on, what nuclear processes are overall. But the development of such a new technology that could transform living conditions, eliminate poverty, etc., this is not something that Zeus wanted to see. Now, who is Zeus today? Well, people like Bertrand Russell fit the bill. I think Russell thinks he might have improved upon Zeus in terms of his evil outlook, his desire to keep most people poor, the desire to eliminate the less desired races, which he was very explicit about, his desire to have a two-tiered educational system, one for the ruling class and one for basically the slaves, even if they were called citizens. That's the empire outlook. And look, it's been succeeding. We've got a massive turnaround with this BRICS development, with Egypt too, etc. But take a look at this. Hopefully you can see this chart. This is a growth rate. This is world population growth rates. Now, part of it's a projection up to 2050, which obviously we're not at. But take a look up to where we are right now, to 2015. You can see that there was a peak of growth rate of population around the time of, excepting for wars, around the time of Kennedy. And since that peak, right at the time of Kennedy's assassination, look at that, the peak was then, we've seen 5 decades of a decline in population growth rate. So these people are saying the world's overpopulated. Well, they're getting their way. World population growth rates are decreasing. Now, why is that? It doesn't have to be that way. Take a look at what we do when we develop a new technology. This is a chart, and the bottom axis is 0. This is the amount of wheat per area of a field in developing countries from 1950 to today. Now, I'm sorry, the base is 500. This has been almost a quadrupling of the yield of wheat in the fields per area, per acre in developing nations over this time. We create resources. Having more people means you have more resources. We are resources. We don't just draw things down from our environment. We create them. So let me go ahead and jump into the theme here of what it means to be Promethean and how we enact that. If we go back before fire or excluding fire, there are simple kinds of technologies that were available. Some of them were these machines. These are called, Archimedes described 6 simple machines. The wedge, which you push in one direction and you split something in a perpendicular direction. The wheel and windlass, you see it here. We can raise things up. The screw, the inclined plane, the lever, the pulley. These things all transform mechanical motion into another direction, make it stronger, etc. Things like that. We're also able to cut and scrape and grind and bend and hammer and chip. There's a lot of physical things we can do with the world around us. We can have agriculture, for example, even without using fire. Let's take a look at a chart of what's possible without fire. What kinds of changes, what exists in the physical world? This isn't a complete list by any means, but physical machines, you got these 6 ones of Archimedes, the screw, the wedge, the inclined plane, the lever, the pulley, and the wheel. And then think about what kinds of properties exist of physical materials. You might talk about the hardness, flexibility, color, density. You can see the list here. Durability, how hot is it? And the kinds of changes that we can engage in addition to the changes of motion, are things that change them physically. Grind, chip, cut, break, bend, mix, heat. That's what we're capable of doing. And when we do those things, we change those physical properties. The physical makeup of something, if you ask what a rock is made of, it's made out of rock. If you ask what milk is made out of, it's made out of milk. I guess you can separate the cream and the rest of the milk. So you might say milk is made of cream and the whatever you call the rest of the milk. But that's what you've got. Now, things really take off totally with the use of fire. There's a lot of things you can do with fire. You can cook food. I mean, just with a basic wood fire. You can cook food. You can boil foods to make them edible. For example, I was looking up lima beans, kidney beans, cassava root. If you can't eat those things raw, they're actually poisonous. Cassava is actually very poisonous. And cultures that use cassava root for their diets, they know that you have to cook it or treat it in other ways to be able to even eat it. So fire just increased our ability to eat, to develop agriculture and other kinds of foods. We can use it to treat rocks so that when we chip them, we get sharper pieces off of it. But the first truly amazingly chemical machine, we're going to compare physical, chemical, and nuclear. The first chemical machine is metallurgy, the creation of new kinds of materials that had never been made before. And as one example, is a great example. So here you got a couple things. We got a piece of copper wire. We've got this green rock. Now, I know you can't see this that well, and even if you could, there's, it looks like a green rock. It looks like a gemstone, some kind of stone you might have on a, decoration or necklace or something, or maybe you'd put it on the outside of a building. It's a green rock. It's not remarkable as a rock. It doesn't chip off very sharp pieces. They're kind of sharp, but not that sharp. It's not particularly heavy. There's really nothing that interesting about it as a rock. Physically, it's unexciting. But, and actually I just did this morning, by applying heat to it and a source of some carbon, and I got a picture of this. I'm sure this is hard to see. We got some sort of blackened copper. The first chemical machine is metallurgy, is turning a rock into not a rock, but a metal. And those are very different things. So I'll show you some pictures of this. So here you've got a before and after picture. On the left you got the malachite and you've got the little bit of copper. To show how we did this, took an acetylene torch. This is not how it was done in the Bronze Age. A charcoal fire was used. Charcoal burns hotter than wood. It's purer than wood. You can't use wood to do this magic trick, to have this new power. You have to turn the wood into charcoal first. So you burn it with an acetylene torch. You can see it ends up melting. You can compare it to the rock next to it, which just stayed as a rock, didn't melt, didn't turn into metal, just a normal rock off the ground. And when we were done, we had this piece of different kinds of copper. Because we were using an acetylene torch instead of a normal charcoal fire, you can see a bright part of copper, and the rest of it's the black form of copper. So this kind of transformation, this was something that was fundamentally new. This isn't a physical change. You can't grind the rock to turn it into metal. You need to have the power of fire, and now the world around you is just transformed. What kinds of changes you're able to apply to the materials around you? Totally new world now. Another example. Let's talk about what that means. Let's talk about what it means to have chemical changes, because with the real development of chemistry in the 1800s by Mendeleev, building on the work of Lavoisier, there was a whole new concept that came about. For one thing, the elements. People didn't think things are made out of fire and earth and air and water anymore. There were specific chemical elements. Those elements were considered the basis of matter because the elements could not be changed between each other. They were elemental. They were fundamental. Rock wasn't made out of rock anymore. It was made out of, for malachite, copper and oxygen. Most rock is silicon and oxygen. So we had these basic elements of materials, and then these elements themselves had properties that are totally different than physical materials. None of the physical words work anymore. So here you've got a chart, and it's comparing three different materials that seem very different physically. Going from left to right, you've got graphite, you've got charcoal, and you've got a diamond ring. So focusing on the diamond part of it. If you look at these properties, they're all very different. The density, charcoal is not dense at all. It floats in water. Diamond's very dense. For the hardness, graphite's soft, charcoal's in the middle, diamonds are, as we know, very hard. And look, the scale is different. For density, diamond and charcoal are the most different in terms of dense and light. For hardness, diamond and graphite are opposites in terms of hardness and softness. The specific heat, or how much energy do you have to apply to change how hot something is, different. Electrical conductivity, very different. Diamonds are excellent insulators. Graphite's a pretty decent conductor of electricity. So physically, these materials seem very different. Charcoal and graphite are both black, so that's similar, but otherwise totally different. Yet, to a chemist, they're all made of carbon. So what's carbon? Carbon's not hard and it's not soft. It's not dense and it's not light. It's not easy to have its temperature change or hard to have its temperature change. It's not a good conductor of electricity. It's not a bad conductor of electricity. None of those words work to describe carbon. We've got a new world and new powers in it. Now we're talking about chemical transformations. So, for example, let's take a look at this. When Mendeleev had developed his periodic table of the elements, he was figuring out something about, for one thing, what the foundations of matter were, and also that there was something higher that united or lay behind the elements themselves. That there was something he didn't know yet about why properties of materials repeated themselves when they were arranged in a certain way that was almost atomic weight but wasn't exactly. Today you've probably seen this table before, at least in a classroom or something. The periodic table as we know it today shows us there's other things that are interesting about matter. So if you take any one of these rows, for example, this row of the so-called halogens, they've all got similar chemical properties. Not physical ones, chemical properties, how they react with other things. So if we were to try to pull all of this together, we've got a whole new vocabulary for the chemical world, a more powerful vocabulary, and we're a more powerful species with the use of chemistry. So here are some of the chemical machines that we use. A fireplace, that's a chemical machine. Just like Archimedes had the a pulley, you've got a fireplace. You've got metallurgy, the first really powerful chemical machine. Since then, we've had the steam engine. We've got a refinery. Here's one amazing thing. Okay, so here's a piece of plastic. I can't really. I like to see a show of hand. Well, let's try it. If you know what plastic is made out of, please raise your hand, or if you think you know. Anybody know? Okay, so now I can't hear you, so I can't hear what your guesses might be, but plastic's made out of petroleum. The same stuff that's turned into motor oil or jet fuel, that's what we make plastics out of. It's totally stupid to be burning it in cars. So anyway, a fertilizer plant, TNT to excavate, to build tunnels and things, a car engine, those are chemical machines. Chemical properties, they're not physical. They're totally unique to the fact that they're chemical. Maybe you haven't even heard of these. I don't know. Enthalpy, that's the amount of heat that comes off in a chemical reaction. Valence, that's related to the columns in the periodic table now, but it was called that before. Atomic mass, ionization energy, Gibbs energy, kinds of bonding. Those are all chemical changes. And you see some of them on the right. Now the higher power of this can be illustrated by the difference between burning coal and using it physically. If you've got a couple pounds of coal, that'll make as much energy as 200 tons of coal pushing down on a lever, or 200 tons of coal pulling down on pulleys. The amount of physical effort that you can get out of that. Like if you had 200 tons of coal, pushing down on a lever, yanking on a pulley to move a train forward, it would move a train just as much as burning 2 pounds of coal. 1,000,000 times difference. That's if the coal is falling through the height of a person. So fire is incredibly powerful. Like Prometheus said, from it we've learned many arts. To go to the next level, this is something you don't see anymore today. This is a watch face that glows in the dark all by itself. You don't need to expose it to light first. It was made with radium paint. Now, before people knew radium was potentially dangerous, the factory workers who made these things did get health problems. But the radiation of radium would be used to make another material glow, fluorescent material glow. So your watch would glow in the dark. You could read it any time of the night. It was one of the first applications of radiation. But now this I do want to talk about in a little bit more detail. How these plants, how nuclear technologies work. So again, let me get if I can get a show of hands here. If you think that the majority of nuclear plants use uranium as their fuel, please raise your hand. If you think most nuclear power plants in the world use uranium as their fuel. Okay, that was supposed to be an easy one, so everyone would raise their hands. All right. Here's the next one. Do most nuclear power plants produce energy by boiling water into steam to blow through a fan? Is that how most nuclear power plants work? It is. Do most nuclear power plants work on the basis of radiation? Okay, gotcha, finally. They don't. Radiation has got nothing to do with the power of a nuclear power plant. Radiation is actually very weak. So on this watch, the radium is emitting little particles which excite the material and make it glow. Radium, if you had 2 pounds of radium, the radiation energy from it would power 50 houses for a year. All of the power in 2 pounds of radium. The thing is, it releases that energy so slowly that you would need 400 pounds of radioactive radium to power your house. If we had a power plant based on radiation, you'd need 400 pounds of radium per person. For uranium, it's even worse. Every person, uranium is not very radioactive at all. If you wanted to use its radiation to just keep the lights on in your home, every person would need 13 tons of decaying U-235 to power their home. You'd need 13 tons of it. So how does a power plant work if it's not by radiation? Well, radiation is only one way, one kind of nuclear change. It's when a nucleus just on its own emits a small piece of something. The way power plants work is when we cause the nuclei to just completely crack in half. Each one of those is much more powerful than basic radiation. And because we can make them occur very quickly, instead of needing 13 tons of uranium with radiation to power your house, you'd only need 2 grams of uranium per year by using fission. So power plants don't work with radiation. It's totally inefficient. They work by causing fissions, by causing the atoms to split apart. And under ideal circumstances, about 2 grams, less than the weight of a penny, is the amount of uranium needed per house in the United States. So that's not very much. You can compare that to 3,000 pounds of coal. So beyond that, when we get to the use of helium-3, and we don't know how to use it yet. We don't understand the mysteries of helium-3. But when we're able to use it, we'll be able to make power directly without having to without having to boil water and make steam and blow it through a fan. Now, this substance, uranium, is physically nothing special about it. Here's some uranite crystals. It's just a crystal. I don't know. It looks kind of nice. Uranium, before the nuclear age, was used to tint glass and give it a yellow color. That was about it. The only physical uses of uranium today are depleted uranium munitions. They use the fact that uranium is very dense and heavy and can burn in air easily, as an armor piercing or for armor. That's the only physical use of uranium. You compare that with the power of it to create nuclear power. So for example, you could take uranium and you could burn it, you could have a fire, and it'll get hot and it'll burn, but you get 1,000,000 times more out of it when you use it in a fission reaction. Just like coal has got 1,000,000 times more power when you use it chemically than when you just use it as a mass, as a heavy thing. One other example on that is in fusion, which is when you put 2 small nuclei together. And this releases even more power than fission. Again, we could make a comparison. When you combine 2 atoms of hydrogen, they make a hydrogen molecule. So the hydrogen gas that's around, hydrogen gas is made of hydrogen molecules, which are 2 hydrogens stuck together. Certain kinds of hydrogen, deuterium and tritium, can be put together in a nuclear way that'll make 10 million times more power than combining them chemically to make a hydrogen molecule. So the same 2 things, you combine them chemically, you get a little bit of heat. You combine them nuclearly, and you get 10 million times more power. So as we discover more about the small, as we develop these higher forms of power, it's just like 6 orders. It's like 1,000,000 times more power, and we can continue this as we move on and discover more. So let me let's look at a chart here. Let's compare the language, the powers of physical, chemical, and nuclear very quickly. So remember, these were some of the words that we used for physical processes. Color, heaviness, density. Physical machines were, levers and pulleys, things like that, bending things, hammering things. That's what you can do in the physical world. In the chemical world, we're able to transform things. You can turn a rock into metal. You can turn oil into a hard piece of plastic that you get used to, build a car or something out of, or a chair or whatever. Totally different transformations, way more power. The steam engine, it's even better than Prometheus giving mankind the use of beasts of burden to do our heavy labor. Coal is an even better beast of burden. And then in the nuclear world, we've got totally new machines that glow-in-the-dark watch, a fusion power plant, nuclear explosives, medical testing like a PET scanner, We can irradiate food so that it's sterile and doesn't grow diseases. We can do cancer treatment. And then again, we've got words that only mean anything in the nuclear world. You don't ask what isotope of rock you have. You don't ask what the half-life of carbon is, at least not most carbon. You don't ask what kind of decay a water molecule has. None of these things mean anything before the discovery of the subatomic world, of the nucleus, and of the power that we have over it. So, how do we make this happen? What is the quality of mind that makes these changes possible? And just to use a very quick example on this, we can compare these two people here. And make this big here. So we've got on the left, we have got Plato, and on the right, we've got Aristotle. This is from Raphael's painting, The School of Athens. And we see three major differences between them: in their hands, in their books, and in their feet. Plato's pointing up. Aristotle is saying, stop. Plato's carrying his book of knowledge with him. Aristotle is holding his book in front of him. I guess he's already reached the pinnacle of all knowledge. He doesn't need to move forward. And he can't, because if you look at his feet, he's standing still while Plato's moving forward. So these two guys, they're both Greek philosophers, but they're not nothing in common. There's American political figures who are obviously very different, such as George Washington and Benedict Arnold. They were both involved in in wars in America. Aristotle believes that all knowledge comes to us from the outside world, that we're born with a mind that is a blank slate, and on it we carve things, we draw things based on our experiences. He says that having repeated experience, you develop from many memories, you develop one experience, and from that experience you learn how things are. You do what's called induction, where from a number of specific examples, you induce a general rule that encompasses them. Now, that's always done outside of sense perception. For example, the simple idea of seeing things that are equal. You never see things that are equal. Maybe today with the factory production, you see things that look pretty equal. You certainly didn't have that then. No two things are equal. Equality doesn't come from observation. It has to come from the mind in some other way. Aristotle also describes what kind of sense perceptions are more beneficial than others. And he actually says this, that although the animals are better than us in many respects, our sense of touch is unparalleled. And it is because we have such a great sense of touch that we're so intelligent. I'll read a quote on that. He says, while in respect of all the other senses we fall below many species of animals, in respect to touch we far excel other species in exactness of discrimination. That is why man is the most intelligent of all animals. I mean, do you ever hear a stupider explanation of human intelligence than that? Plato, on the other hand, through Socrates, Plato was a student of Socrates and wrote down discussions that Socrates was involved in. So Plato's dialogues include Socrates. He took a very, very, very different view. He said that the mind, in some sense, already knows everything. That our soul already has imprinted on it the entire universe, that it mirrors the whole universe, and that when we make discoveries, we're not so much getting something from outside that's coming into us, as we're remembering something that was already in us. A famous example of this is in his Meno dialogue, where he uses one of Meno's, a rich guy, uses one of Meno's slaves who never got an education in geometry. And Socrates works him through a geometric discovery, at the end of which the boy is certain that he knows something about squares and areas. It's a tricky problem. The important thing isn't so much the specific answer about doubling the square that the boy figures out. It's that he knows he's right. Now, knowledge, certainty, conviction that you're right That doesn't come from outside. It might for a student of Aristotle who says, well, if my teacher told me so, everybody tells me I ought to listen to this guy, everybody thinks such and such is true, therefore that's the authority. Socrates says that authority comes from within. And that means that all people are equal. Every person has that potential ability to make a discovery, to go beyond their senses, to discover why things are the way that they are, something that's never suggested or given to you by what you see. You elicit it that way. But then that conviction that comes from that knowledge, that is an internal sovereign thing. That is what distinguishes us from animals. That's the important thing about knowledge. He says that our senses help us elicit these recollections, but they're not the basis of where knowledge actually comes from. Just wanted to show you a picture of this. This is Aristotle applying his theory of knowledge. This is a famous painting. This is called Aristotle Contemplating the Bust of Homer, although it looks kind of like Homer is contemplating Aristotle. So Homer's the blind poet, the creator of the Iliad and the Odyssey. I guess Aristotle's trying to figure out how he thought the way he did by using his sense of touch, feeling his hairdo there, and by looking at him, although Aristotle looks somewhat absent-minded, and I don't know how well you can see the image. If you get if you look it up and get a closer look at his face, he looks kind of clueless and depressed and sort of sad that he can't feel things through the hair properly. That's what it looks like to me. And Homer, you can see the eyes aren't really drawn in that bust, but it does look like he's looking at Aristotle, and I'll leave it to you to think about what he might be thinking about this this weird guy feeling his head. And then just the very last thing on that, just to say a couple of words about Cusa and about the creation of the Renaissance and about a Promethean outlook, is that Cusa is very clear that truth is known only imprecisely, for one thing, but the truth is known by contradictions. The exact opposite of Aristotle, the exact opposite of logic. Logic doesn't make a discovery. No one ever made a discovery by logic. They might realize they don't know something. You can use logic to know that you don't know something. You never use logic to make a discovery. You never use mathematics as the form of making a discovery. Never happened, never will. Cusa says very directly that Aristotle is a fool on this account, and he says that it's only when we use contradictions between our senses, not a repeated observation that we then induce something general from, but exactly the opposite. That when we look at our perceptions with our way of understanding them, and we find contradictions, when we find things that don't work, that are unexpected, that are surprises, that we can't explain, that's where new knowledge comes from. And when we create that new knowledge, it doesn't come from explaining in a general way what we observed. It comes from going beyond that to say, why are these observations occurring? Why is this process occurring the way that we end up observing it? And that has been the basis for these developments in science that have led to these higher forms of fire, of the chemical knowledge, of nuclear knowledge. It came from the basis of science, Kepler, and real physical astronomy. That's how those steps get made. And what we've got today is a real dead end in science. We've got a lot of potential from the problems left by Planck and Einstein that are unresolved, that aren't answered. How do general relativity and quantum theory work together? Are things particles or waves or both, whatever? That's not resolved. And the work of Vernadsky has not been fully applied to these problems. And if we do that, we've got a potential for having a whole slew of fundamentally new discoveries about the world around us, including possibly some answers to what's troubling us about fusion science might lie in the domains of biology, or even insights gained from human economics, cognitive processes, to an understanding about how the universe works as a whole. So let me stop with that. Thank
Okay.